So in the previous video, we saw the condition of constant acceleration, and we could see if we know acceleration, how we can get to positions and velocities using those constant acceleration equations. But often, the acceleration is not constant. What do we do? And that is the case of just a random motion, or we can call it erratic motion. And let's see what we can do. So imagine, well, we know that velocity is time derivative of position, acceleration is time derivative of velocity. So if somehow magically, using a measurement system, that's not good. Using some kind of measurement system, I have measured position as a function of time, and maybe it looks like this. The position increases, reaches some maximum, and then falls down. What can we do? Note that velocity is time derivative of position, and time derivative means slope. The slope of that's too tiny. The slope of ST curve. And that's what we can do. We can take derivative or find the slope of S curve at any point. And that should give us the velocity. So all of these slopes are a measure of the velocity. And we can continue and plot now velocity as a function of time. So at any of these points, at the beginning, I have a relatively large slope. So velocity is kind of positive like this. It decreases. This slope is decreasing. So I have smaller and smaller velocities. And after some point, this slope becomes negative. This is a negative slope. And my velocity is negative. So if I try to draw this, something like this, I can both graphically, and if I know the equations, obviously I can take analytical derivation to get to velocity. And I can keep going to get to acceleration. Acceleration is the slope of, let me write it down, the slope of VT curve. So I find this slope. Well, the way I drew it is almost constant. All of these are negative, relatively constant. Maybe it increases or becomes a bit more negative as we go along. And this is my acceleration. So the slope becomes these values. And that's how you can both graphically, and if you know the equations, analytically, take derivative to go from position to velocity to acceleration. You can also go back if you know the acceleration. Somehow somebody has given you acceleration. Let me draw a positive acceleration. Something like this. Acceleration as a function of time. Integral means area. So you can take the area on the curve. Like this. And that area, remember area, does not give you the value, it gives you change, delta V. So you need to know the initial velocity. So let's pretend we start from some V naught. That's what we know. And after this time, my velocity increases to some amount. So it goes up like this. And this change is the delta V I calculated as the integral. If I go to a later time, let me draw it with a different color. And I take the new integral, that gives me a bigger delta V. And continue something like this and keep going. So now this is my green delta V. So area under curve gives us change in velocity. And similarly, integral is area under curve of AT. The integral of VDT is area under curve of VT. Going back maybe to red. Now I can take area under this VT curve. This is time. To get S, again, you need to know where you start at the beginning. You need to know S naught. This area gives you delta S. So it's a positive value. You're going to have some delta S. So you'll end up, I don't know, somewhere here. Oh no, too far. You end up here and so on. You likely have a lot bigger area here. This is the green delta S at a later time. So you change your position even more, maybe this much. This is green delta S, and so on. And you can construct your position curve as a function of time using the integral or concept of area under curve. Or again, if you know the equations, you can analytically take the integrals. Yeah, let me add one other thing. Could be interesting and informative to see. This erratic motion, this method, taking derivative and integral, obviously works for any condition, and that includes constant acceleration. In such case, for instance, if I have my acceleration, it is a constant value at AC. And you start from some V naught. This is a little, let me draw it slightly better. What happened? This is V. I start from some V naught. So at any time, this area, if this is time, this area is AC times T, the width and height of the rectangle. And I go up that amount. So this becomes ACT, and the final value is ACT plus V naught. And my velocity will become just a straight line, with the slope being AC. And then you can take the position. Oh, why is it not cute? You can take the position or integral velocity to get to the position at any time t. You have this area that you need to find the integral, and that is t times V naught plus the other one, V naught plus AC, over 2. And that is the same equation we had before. That is, because we have 2 v naughts here, they cancel out with the 2. I have v naught t plus 1/2. Oh, there's a t here. 1/2 ACT squared. I'm calculating the area of that trapezoid. And starting from some S0, I have a quadratic curve that increases like that. So you can see it. These equations are also possible to calculate just using graphical method and area on the curve. So I think that is all I have for this section. We look at a lot more examples in class, and that should be it for this. All right, I'll see you then.